All right, here's the second video for 2.6 special functions. And so we're going to do two different examples. The first one involves absolute value functions, and that should be kind of self-explanatory. They're functions where there's absolute values in there. So here's the example. F of x is the absolute value of 2x minus 6. All right, so how do we handle graphing that? So here's the steps, and it really always will work like this. You can always do it this way. So read these real quick. Pause it for a second and read through it. So step one, I take what's on the inside. So, and I don't have a marker. 2x minus 6 is what's inside the absolute value. All right, and you want to figure out when it's equal to 0, because that's where basically these always look like V shapes, and that's where the corner of the V is. So linear equations make straight lines. Absolute value equations, or at least the ones that we'll work with, always make V shapes, or potentially upside down V shapes. Okay, and the corner will occur whenever 2x minus 6 equals 0. So we get 2x is 6, and so x is 3. And so, oops, I kind of spoiled it over here. What you'll then do, forgot to cover this up or something, you'll use an XY chart, making sure that it's centered around the number you just got here. So, the reason why this middle number is a 3 is because what you got here. Okay. You need to plug in a fraction sometimes, that's fine. Because, well, actually, even though you're plugging in a fraction, you'll know that it will end up giving you 0. Because that's what you just figured out here. It'll give this chunk here 0, no matter what. That's what this work in the blue was telling you. So you know you're going to get a 0 in this middle one. All right? And you just pick whole numbers that are easy to plug in near the number you found right here. So 2, 1, 4, 5 are choices that make sense. You don't have to do that, but you can. And so then what you do is you just do what you do for any XY chart. You just plug in the numbers. So 2 times 1 minus 6. You do, I'll show the work here, or at least the first two, and then hopefully you guys get the drift. So you do 2 times 1 minus 6 is negative 4. So absolute value of negative 4 is 4. All right, so you put a 4 there. Okay. Then you do 2 times 2 minus 6 in absolute value. So it's 4. It's 4 minus 6, so that's a negative 2 in absolute value. So you get 2. Okay. One more, and then you guys probably would be a good idea to just pause it and do it yourself. But I'll do one more. Two times 3 minus 6. So you get absolute value of 0, which we just figured out. That's what the blue down here really figured out, is you're going to end up getting 0. The 2x minus 6 will be 0 there, which is 0. Absolute value of 0 is 0. All right, so you might want to pause it and see if you can figure out 4 and 5 on your own. And then, so pause it now if you're going to do that, which I recommend. I'm just going to write in the answers. Okay, so that's what you should get. So then you just plot those points. So 1, 4, maybe, something like that. 2, 2, 3, 0, boom, boom. And like I said, these are just going to be straight lines. Well, 2 straight lines that make a V shape. And so that is what they should look like. All right, let me clean it up. There you go. That's really kind of ugly, but oh well. All right. Okay, I paused it and cleaned it up a little bit because it looked pretty bad. But I take these 5 points and they make that kind of V shape, and there you go. That is the absolute value of 2x minus 6. All right, so the other type is probably pretty challenging, and I don't know how much you did with these in Algebra 1. Maybe none, so we'll see how this goes. So piecewise defined functions. So piecewise defined functions are ones that when you graph them, you get different pieces. You get different shapes depending on which part of the domain you're in. So in this example, when x is greater than 0, when x is less than 0, that's right here on the top one, you use the formula 2x plus 1. If x is greater than or equal to 0, you use a different formula, you use x squared. So it's two different formulas for the same function, which is really weird. Back here, boom, just one formula for this function, right? We use one formula to figure out all these y values in blue. Here, we're going to use two different ones depending on which part of the domain you're in. So remember what domain is. It's the x's that you can plug in. That's the domain. So if the x's are less than 0, if you're in that part, well, then use 2x plus 1. If you're in the other part, you use x squared. So let's just do that. So hold on, let me pause it real quick. All right, I paused it to include these little arrows and the braces here on the right. So the red arrow is pointing to the top two, because you're going to use the 2x plus 1 for these top two. All right, the green arrow is pointing to the bottom 3, because for the bottom 3 in our xy chart, you're going to use x squared as a formula, excuse me. So then you just start plugging the numbers in. So 2 times negative 2 plus 1 is negative 4 plus 1, so negative 3. Then you get 2 times negative 1 plus 1, and you get a negative 1. Okay? So, in fact, it should make some sense. You don't really even need an xy chart. It's a linear equation. So you might just know that, it's a straight line. It's a linear equation, straight line, whose y-intercept would be 1 if it actually hits the y-axis, which it doesn't because it stops before 0, and its slope would be 2. So I'll draw this in red, and it looks like this. All right, I'm not even thinking about the points. I'm thinking about the fact that it's 2x plus 1. It should be a linear equation. Okay. In fact, actually, eek, too big. That y-intercept is not included, like I was saying, and I need to indicate that with an open circle right here. So the y-intercept is not at 1. It would be because it's 2x plus 1, and usually, this number here indicates the y-intercept, but this stops before it hits the y-axis, and the way we have to indicate that, the way we have to communicate that is this less than 0 business right here. And so now we use the green, or the bottom formula, the quadratic, the x squared. And so let me write that in there. So it's 0. Don't really need to do the parentheses, but I will, because I tell you guys to always use parentheses. So 0 squared is 0. 1 squared is 1. Hold on. Still getting the hang of this action. Hang of this. Alright. 1 squared is 1. And then 2 squared. Okay. 4. So you get 0, 1, and 4. And if we did another one, if we count the numbers, actually there's a better way to do this than what I'm doing, so let me back it up. Let me just use the stupid mouse. It's better. 1, 1, and 2, 4. 3 squared is 9, so heck, I'll put that one in there. If I continue the XY chart just one more, we get a 9 there. And that's fine, it's not on the XY chart, but we can plug, we always use this formula as long as x is greater than 0. So 0, 1, 2, 3, pretty good, that'll work. And so, let's see how this goes. We have a parabola, maybe, if I can sketch it. Oops, it's not working too well. Let me back it up. Maybe I'll use mouse. Maybe mouse will look a little better. All right. Well, shoot, not too good. But it's supposed to be right inside of a parabola. Let me pause it and make that better. All right, that looks a little bit better. But there you go. So the red is the linear part. It's the 2x plus 1, and the green is the quadratic, the x squared. You know, it graphs as a parabola. And this is a piecewise divine function. Okay, each piece can be whatever, and you get more than two pieces. You have as many pieces as you want, and you just have to plot the whole mess of points to get all the different pieces. All right, so it's a linear equation while x is less than 0, and remember what happens is x is less than 0 over here on the left of the graph, so that's why it's a line on the left side of the graph. Then when x is greater than or equal to 0, you get x squared, which is a parabola, and that's why it's a parabola over here on the right. So there you go. Hopefully that's enough to help you with piecewise defined functions.